Hello everyone, now I want to discuss the nomenclature, the names and the formulas for a different kind of compounds. What we call it molecular compounds is when covalent bonds are formed, they are quite different from the ionic bonds, and hence the ionic compound and the covalent compound, sometimes referred to as molecular compounds, quite different from each other in terms of properties, and from the key difference in properties such as the charge or lack of the unique nomenclature, the naming systems. The naming system has to be devised for molecular compounds. As we can see on this, another start with the periodic table. On this periodic table, whether the element is going to have a totally transfer of electrons between them to form positive charged ions and negative charged ions to form the ionic bond. And so, actually a lot of the connections between atoms resulted in not complete transfer of electrons, not formation of the ions, but sharing of the valence electrons, and hence the covalent bond, So if, as one indicated, let's take a look at a kind of what we call it a classic example of covalent bond. If we're looking at two chlorine atoms by each other, each one of them will have 7 valence electrons. By the 7 valence electrons, how could they get to 8? So it's driven by the octet rule again and again and again. So the best way for them to do is actually start sharing a pair of electrons, and so both chlorine atoms will have 8 valence electrons, and hence very stable. But as you can see, one of the characteristic associated with that is this pair of shared electrons. So there's no complete separation of shared valence electrons, and that posed an issue for naming the molecular compounds, since they do not have complete charge separation. So we do not have cations or ions. Okay, you don't have them. But remember, in the ionic compound, for the ionic compounds, it's self-evident because the total positive charge from the cation has to match. Total positive charge has to match equal to total negative charge. So total positive charge equals to the total negative charge. So there's no clear indication of how many of each individual ions present in each formula unit. However, it can be easily derived by taking into account of charge of each individual ion, and the ultimate goal for any system is they have to be equal to 0 in net, which means the total plus charges will be cancelled, will be equal to the total negative charge. So there's no need to tell how many cations you have, or nor it's necessary to tell how many anions you have. So it's automatically building. However, we are facing a dilemma now, since no charge separation molecular compounds. So a different system has to be devised, and here comes the different system. So literally we have to tell how many no charge molecular compounds, have to tell how many each element are there in the compound. Let's take a look at example. One of the classic example will be water is H2O. Is if actually I draw the structure, will be covalent bonded to the oxygen for the H. But there's no way, there's no positive charge or negative charge associated with that. So then other names has to be devised to ensure the proper communication of chemical information. So in this case, it's going to be called the prefixes. The prefixes will be used. So the prefixes, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 1 we call it mono, 2 we call it di, 3 we call it tri, 4 we call it tetra, 5 we call it penta, 6 we call it hexa, 7 we call it hepta, 8 we call it that's not the 8. 8 is what we call it octa. 9 is called nona. 10 is called deca. For this, there's no shortcut. You have to memorize them all. The format is we use prefixes, and first element assumes the same name as the elements. Okay, so second element has to assume the IDE notation. And with one exception. If 1 is the coefficient for the first element, it is dropped. Please remember, this is the only exception for molecular compound. Only exception for molecular compounds. So hence, what do we call it? The water, the official name should be 2 hydrogens. So it will be dihydrogen, monoxide. There's only one oxygen. So this mono comes in and have to turn into the IDE. Let's take a look at some examples. As we said, we have to tell how many of each element there in the compound. So then we can take a look at it. This one is called a dinitrogen pentoxide. So you will have 2 nitrogen elements or ions and 5 phosphorus and 5 phosphorus. And in this one, it will be aluminum peroxide. Oh, so sorry. This is not correct. And what I want to say here is, let's skip that. But it's much easier. Well, let's do this. Carbon dioxide, as you said, it should be a carbon, it should be monocarbon dioxide, but the mono got dropped, so then it will be carbon dioxide. And this one should be SO3. So if we see a formula SO3, you'll notice there are 2 nonmetals, sulfur and oxygen, fairly close together. The electronegativity fairly close together. So there's covalent and bound. No charge separation, so it's hard to tell. So this one should be called sulfur trioxide. It's the same approach here. This one will be sulfur hexafluoride. Okay, and with that, I wrap up my podcast. Please complete questions on appropriate worksheets. Thank you very much for your attention.